Okay, good morning, folks. Again, my iPad seems to be failing me today. It's a rather simple task to open PowerPoint, but it doesn't seem to want to do that. So we're going to be working off the laptop today, which means whatever writing I'm going to be doing is going to be on the board. And for some reason, I also can't see presenter view, which is also a little bit frustrating for me. So let me try to do that first before we get into it. Why does presenter view not show up here? There we go. Well, even then, presenter view still doesn't work. So we're going to go through it as best we can today. So since last day, a few more people answered. Thanks for that. Please, if you haven't answered the student opinion survey, please just use the QR code to visit the site and fill out the survey. We're in the last full week of classes today, and we're also starting a new topic. The last several months, I suppose, at this point, we've been talking about all the different components we might see in our structures, and whether we've got a tension member, a compression member, or a flexural member generally depends on, first, what the purpose of the member is and what the structural analysis results are. And so we've looked at tension members, which might be a brace that experiences tension. Maybe it's part of a tension-only bracing system where only the tension brace works. Maybe it's a part of a tension compression bracing system where we have tension members that are sometimes in tension and sometimes in compression. We also have columns that predominantly carry compression, and then we've got our joists and girders which carry flexure. So we've, I think, successfully looked at all of the individual components so far in our structure that carry basically one action. Okay, so we either have just tension, just compression, or it's just working as a beam, and I guess in that case, technically, there's shear and bending that we need to consider, so we looked at the shear resistance as well as the bending resistance. Today, we're going to start looking at what happens when we have combined loading effects, and so we're going to focus first on what happens if there's a member that has bending, maybe it's from transverse loads like a uniformly distributed load or point loads, as well as tension. Okay, so some members will carry tension and bending. We're going to spend a couple days looking at compression and bending, which focuses a little bit on something called the P-delta effect and local member stability. And that's pretty much going to be it for this course. Okay, so we've got 3 full lectures left of new material. At the last day, we're going to just wrap things up. On Monday next week, I'll talk a little bit about the exam, what to expect, and I'll also use it as an opportunity to just kind of bring the entire course to a close and bookend the course with the introductory lecture, okay? So today we're going to be focusing on members that carry combined loading, just introducing the concept today, but we're going to be seeing a whole bunch of different equations that look a little bit funny. Usually we calculate MR, make sure it's less than or equal to MF. Sometimes we calculate CR, make sure it's less than or equal to CF. What we're going to be doing from now on is calculating TR and MR or CR and MR, and we're going to take the combined utilizations, so to speak, and these are called interaction equations. So basically what we have is a CF over CR ratio, a TF over TR ratio, some MF over MR ratios. And if you think back to what we've been talking about in STAD Pro, if you had a tension member and you had TF and STAD calculated TR, it presented the utilization ratio, which was TF over TR. Maybe it was 80%, 90%. And so basically what we're doing is we're calculating the individual utilization ratios for the individual actions present on the beam until we get into beam columns where it looks similar, but we're going to see that there are some nonlinear interaction effects that we essentially simplify with some straight lines, and that will be the topic of Wednesday and Friday. But today, for the most part, we're focusing on this combined interaction equation here where we're going to have a tension force, some bending, potential for bending about the 2 axes as well, not just strong axis bending that we'd expect in a typical joist or girder. Okay, so this is kind of an introduction to combined loading. There are lots of different members throughout our structure that will experience combined loading. Sometimes they're little stubs like this. When I introduced tension members and bolts in tension, I showed this image before. This is from the school on the north side. This joist and this girder are supported by this hanger. And before I said maybe there's just a tension force on this hanger, but if we were to consider the eccentricity of the load comes on the connection, which is a little bit out from the face of the support on both sides. maybe there would be a little bit of bending as well that we would consider there, and that would be a member that we'd consider to be under combined tension and bending. Maybe we're looking at a braced frame, and we know that these, which are essentially girders or joists in some sense, depending on which way everything's oriented, this is basically a beam that's responsible for carrying some gravity loads, some shear and bending. But at the same time, when this brace goes into tension and this brace goes into tension, those two tension forces are going to be applying a compression force to the beam in addition to whatever bending's there. So that member is going to see a combination of flexure and compression, and we have to consider the combined effects of those two actions. Most common, which is something we're not really going to deal with in this course, but in an industrial structure where you're trying to lift and handle material using different kinds of cranes. This is a crane that's supported off some crane supporting columns. This is a column that also has a little standoff here. So in addition to whatever compression this column is going to support from the crane carrying the load, the fact that the reaction is at an offset from the face of the column is also going to introduce some bending. And so that's another example of where we might have strong axis bending paired with compression. And so that's a situation where we would have some combined loading. Another situation which might make a little bit more sense for us, we've got perhaps a structure. This is maybe the face of a building. And these are little members, they're called girts. Basically what they're there for is to support some glass glazing. And so these columns that are responsible for carrying the gravity load from the roof, they're also going to be carrying point loads, which are the reactions from these girt members. If there's wind blowing on that wall, there's going to be some bending applied. And another situation, similarly, a glass facade supporting system frames into the columns again, so this column would be carrying axial force from the gravity loads on the roof, as well as whatever point loads come into these little glazing supports because of the wind pressure acting on that outside wall. Okay, so those are some situations where you might have combined loading. So you should be able to identify some situations where we might have members responsible for carrying combined axial load and bending. We should be able to describe some of the mechanics behind the interaction equation that we're going to talk about today. That's the TF over TR plus the MFs over MRs. And most importantly, you should be able to apply this linear strength interaction equation. And also, we're going to talk very briefly about a plastic strength interaction equation. And you should be able to figure out which of those two you should be applying, where you'd find that in S16, and how you'd use that to check a member that carries a combination of tension and bending. Okay, so we have some members that might carry tension and bending. We're going to look at how we calculate the strength of those members today. Does anyone have any questions about these three things before we get into the technical material for the morning? Okay. Is Pull Everywhere going to work for me today? For some reason, I find it's unlikely, but I'll give it one shot here because it's more likely to work for me on my laptop than it is to work on the... Oh, great. Okay. Well, let's just skip that, and I'm going to ask the question instead. Why is my PowerPoint not keeping up with me here? There we go. So before I get into that, maybe I'll just draw it on the board. So we've got a member. Let's just say that this member is responsible for carrying a bending moment. And maybe we've got a member is responsible for carrying a bending moment as well as some kind of tension force that might be present. They're both the same length. I didn't mean to draw them that poorly. But on the left-hand side, bending only, right-hand side, tension and bending. Between these two cases, do you think that moment only or moment and tension is going to end up in a worse scenario for that beam in terms of the strength? Hands up if you think bending only is going to be worse. Hands up if you think bending and tension is going to be worse. So we'll see. This is kind of a trick question. And so we're going to see that sometimes tension and bending is worse and sometimes tension and bending is better. I saw a hand up from Josie for bending only is better. Do you want to take a shot at why, or share with the class why you thought maybe bending only would be better?
I don't really know. I was just picturing that if like a member's already like taught, like if it's in
it does make it more stable and it makes it stiffer, right? If you have something bends, it bends down, then you pull it, the deflections are a little bit better. So we're not really going to talk about the deflections as much, but certainly that intuition that it's more stable and maybe stiffer is correct, okay? In terms of strength, though, we're going to see that it depends on what we expect the beam to, what kind of limit state we expect the beam to fail under. So if we expect the beam to fail in yielding, then the bottom flange, we're going to see in a minute, is going to carry more tensile stress. But if we expect it to fail in lateral torsional buckling, which comes from excessive compressive stress on the top flange, that tension is going to take some of that compressive stress away from the beam, and we're going to see it's less likely to experience lateral torsional buckling for that reason. Okay, so if I asked you to calculate the stresses, the normal stresses, in a member with moment and tension, and let's just say I only care about the normal stresses, okay? So at this point, I hope you're all still familiar with the differentiation between shear stress and normal stress. Where is the maximum tension stress on that beam? It's under uniform bending and tension. Where's the maximum tensile stress on that member? Well, if we look at this and we were to take a cross-section through here, we draw the stress diagram, there's going to be some tension, right, here, and there's also going to be some bending. So I'll draw it, I suppose, this way. On the top, we've got compression. On the bottom, we've got tension. As long as the member responds in the linear elastic range, we can apply the same concept of elastic superposition to add these stress profiles together. This is definitely something you should have done in 2023. Whether or not you did it is sometimes a mystery to me. Do you remember doing these kinds of problems in CE 2023? Adding the normal stresses? Good. So we've got tension stress from the actual applied axial force. We've got some tension stress and some compression stress from the bending that's applied to that section. So let's remember some of the things that we talked about in the course already. We'll just remember from 2023 even that the stress acting on a section is the applied force over the area, right? P over A is probably what you did in mechanics of materials. And we'll call that axial stress just FA. It's the axial normal stress from the applied tension force. And then we'll look at the bending stress. And so we've got some tension up here and some compression over here. And normally you would have calculated the bending stress my over I, right, in mechanics of materials. But we'll remember that in this class, we defined a new term, right, the bending stress. Well, actually, you would have written it as sigma, I guess, is my over I. Or remember that we defined a new term in this class, the section modulus, the elastic section modulus is I over Y, and so we can write this as M over S. Okay, so the bending stress at the extreme fiber, anyway, is equal to M over S, and we'll focus on strong axis bending for now. Okay, so the tensile stresses are in blue, compressive stresses are in red, and as long as these don't exceed yield, in combination, we can apply the elastic superposition, and we can say, okay, the total stress on the tension flange is going to be equal to the stress from P over A plus the stress from M over S. And then the stress on the compression flange is going to be just the total compressive stress from bending, M over S, minus the tensile stress, T over A. Okay? Are there any questions about this concept before we continue? It's very important. You should have already seen it before, but if you have any questions, you should ask them now. Okay. So we've got two areas to look at. The first thing we need to look at is the stress in the flange and tension going to exceed yield? And for the most part, for most sections, generally speaking, we start with the proposition that we don't want to have the cross-section start to yield anywhere along the section, and so we're going to look at preventing yielding. And so if we have this equation, we can say, okay, MF over S plus TF over A, that shouldn't, as a combined tensile stress, exceed the resistance factor times Fy. Okay, so that's the first limit state we're going to look at, and that's called cross-sectional strength. We want to prevent yielding of the flange experiencing the highest tensile stress. We calculate the stress as M over S plus T over A shouldn't exceed phi Fy. If we rearrange some things here, I'm just going to take this and divide everything through by Fy. So on the right-hand side, I'm going to get 1. On the left-hand side, I'm going to get phi Fy times Sx, phi Fy times A. And that's kind of convenient for us because we've already talked about what phi Sx Fy is and what phi A Fy might be. As written there, phi Sx Fy, what does that represent in terms of things that we've already talked about in this course? We use phi S Fy to calculate the moment resistance of class 3 sections, right? And that corresponds to reaching, limiting the moment resistance to the yield strength or less. And so that's moment resistance calculated in accordance with clause 13.5 for a fully laterally braced beam if it's a class 3 section. And the other term, we've got a denominator that we talked about a long time ago, way back in lecture 11. We have the yield, gross yield resistance of a tension member, right? Phi A Fy was the gross section yielding resistance of a member in tension. And so we can rewrite this basically as MFX over MRX, though it's very important to remember what MRX this represents. This is the moment resistance of a class 3 beam calculated in accordance with clause 13.5. And then we've got TR representing the gross section yield resistance of that cross section. Okay, so if we've got just tension and strong axis bending, in order to prevent the tensile strength from exceeding the yield, or the factored yield strength, we take MF over MRX plus TF over TR. And as long as that's less than or equal to 1, we're preventing yielding from developing on that flange. Okay? Are there any questions about those concepts before we continue? So that's the tension flange. We want to keep the tensile stress within the maximum yield stress limit. The other thing we need to look at is the compression flange. And as we've talked about before, when the flange is under compression, it wants to act like a column. The top flange wants to buckle it wants to buckle laterally, resulting in torsion of the section. And generally what we call that is lateral torsional buckling. So what we want to do is make sure that the compressive stress is less than or equal to whatever compressive stress on the flange we might consider would cause lateral torsional buckling. Okay, so when we have lateral torsional buckling, we do something like, we calculate MU, and we calculate maybe for a class 3 section MY, and then MR might be phi MU, or MR might be 1.15 phi MY times 1 minus 0.28 MY over MU, or something like that. Or we could get to the fully plastic state. But in our case, we're assuming that the compressive stress in the flange is going to cause one of these two things to happen, either elastic lateral torsional buckling, where MR is phi MU, or inelastic lateral torsional buckling, where MR is calculated using this equation. What we're going to do is we're going to say, okay, what's the moment resistance of our beam associated with the potential for lateral torsional buckling? Either it's phi MU or this long equation, and that is a moment that would cause lateral torsional buckling. What we're going to do is we're going to use that moment, and we're going to divide by the elastic section modulus to get the critical compressive stress that would cause that moment to occur. Okay, that stress would cause MR to develop, and that would result in either elastic or lateral torsional buckling. So if we back calculate a critical stress, as long as we don't exceed that amount of compressive stress in the flange, we won't experience lateral torsional buckling. Okay, so just a bit of back calculating the equivalent compressive stress associated with the lateral torsional buckling limit state for a beam. So what we're going to do is we're going to make sure that the combined stresses, MFX over S, X minus TF over TA, that shouldn't exceed that critical stress, and we're going to call that MRX divided by SX. So if we rearrange that equation, we get something a little bit funky looking, but we divide through by mrx over ss f over sx. Sx goes away, we end up with mfx over mrx, and then we get this weird thing, tf sx divided by mrxa. Okay, and that's kind of a weird ratio. It doesn't mean a whole lot to us, but as long as these two ratios, one subtracted from the other, is less than 1, we're preventing the compressive stress from exceeding the compressive stress that would instigate lateral torsional buckling and flexural failure of the beam. Okay? Does anybody have any questions about that rearrangement of equations or what that expression represents in terms of the limit states before we continue on? So we want to prevent yielding in tension, and we want to prevent lateral torsional buckling that happens when we get a certain compressive stress developing in the compression flange. Okay? We also could introduce whatever weak axis bending we might get. It's more common to just have strong axis bending, but from time to time you may have a little bit of weak axis bending as well. I'm just going to add that in there as another stress to consider. Basically, if we're looking at the combination of strong weak axis and tensile forces acting on the cross-section, we get this crazy-looking section where we have a linear stress profile. We've got a peak compressive stress down here that corresponds to the two moments added together minus the tensile stress. And then up here we get the two moments together plus the tensile stress. We want to prevent this from yielding. We want to prevent that from exceeding the stress that causes lateral torsional buckling. And so what we have to check for strength is we have to check this interaction equation. We have mfx over mrx, where mrx is based on fully braced beams, and we have clause 13.5. And most importantly, for this equation, it's with a class 3 section, so mrx is phi sx fy here, phi sy fy here. We also have to check stability of the beam, right? So we've got lateral torsional buckling to consider. We've got the same equation, or a similar equation, the two moments added together. But it's important to remember that this MR is calculated using clause 13.6. Okay, it's the moment resistance that is associated with lateral torsional buckling. So it's important, despite the fact that we've got two MRs here. One is for fully braced yield moment resistance. The other is for unbraced lateral torsional buckling resistance. Okay? So depending on which you're checking, depends on which moment that you're calculating. Otherwise, all the other parameters tend to stay the same. So we kind of get back to the pull everywhere question. What happens when we have tension? Does that make things better or worse? For strength, it makes things worse, right? Because we're adding tensile stress to a section that already has bending on it. That's down here. But for stability of the beam, for lateral torsional buckling, the presence of tension helps to reduce the overall compressive stress on that flange and reduces the potential for lateral torsional buckling. Okay, so sometimes it makes things worse, sometimes it helps out a little bit. Any questions about these concepts before we continue? So that basically brings us to how S16 presents the requirements for the steel members that carry axial tension and bending. And what we're going to see is the same equation, and it's going to say that for members in general, we have to check strength. So we've got TF over TR plus MF over MR plus MFY over MRY. That has to be less than or equal to 1, where MRX is the strong axis moment resistance calculated in accordance with clause 13.5. Right? That's because when we derived this equation, it was based on the bending stress, where we calculate the stress as M over S. And the weak axis moment calculated in the same way, just with SY instead of SX. Okay, so we've seen this before. For laterally unsupported members, we have to check stability. Okay, so basically this is the equation that we derived already. MFX over MRX, MFY over MRY, minus TFSX divided by MRXA, where MRX is calculated in accordance with clause 13.5. Now that applies for class 3 and 4 sections because we're working with elastic stresses, and so when we add these together, we base it on S. If we have a class 1 or 2 section, we can simply replace S with Z, both in the moment resistance calculations and in the interaction equation up here, TFZ over MRX over A instead of TFS. Okay? So we still have the stability check where we're adding the stresses using linear elastic superposition. For class 1 sections, we just replace Z or S for Z. Should be pretty clear so far. When you read clause 13.9.2, which is for class 1 and 2 sections of doubly symmetric eye shapes, then things start to look a little bit different. We've got TF over TR plus 0.85 MFX over MRX plus 0.6 MFY over MRY. That has to be less than or equal to 1. And then it's also going to say, well, you should check the interaction equation without any tension, just based on MFX over MRX plus MFY over MRY. So that might seem a little weird. Like, why are we reducing, effectively, the effects of the strong axis moment and weak axis moment by basically taking 15% away from the strong axis bending stress and 40% away from the weak axis bending stress? We haven't talked about that. Why would we do something like that? The correct answer should be, I have no idea, because you've never seen this before. Okay? So what's going on here? When we have class 1 and 2 doubly symmetric eye shapes, we tend to no longer work with the linear elastic bending stress profiles anymore. We work with the plastic stress distributions. Okay, so we've seen this before, not in 3D as I've drawn it, but on the top we have the tensile stress exceeding yield. It's always going to be a uniform profile whether we are exceeding yield or not. But when we have a class 1 or 2 section, we deal with the plastic moment resistance, which corresponds to a plastic tensile stress below the neutral axis and a plastic compressive stress above the neutral axis. Okay? Now, we can't just add these together. We are no longer in the range where elastic superposition is applicable. We can't just take the tensile stress and add it to the bending stress, because if we take this and add it to this, all of a sudden we have 2Fy in tension. Can't do that. Can't exceed the yield resistance anywhere in the cross-section. What we need to do instead is figure out where is the neutral axis going to be such that we develop some tension, and at the same time, what is the corresponding moment on that section? I go into this exercise in much more detail in 5063. It's not really, I would say, worth it to us at this stage to go through it. What I'm trying to communicate here is elastic superposition is no longer applicable, and the problem is different. We've got a plastic stress distribution to consider, and what we're going to do is just shift the value of y. If y is 0, we have pure bending. If y is d over 2, we have pure tension. And as we change y, we're going to get a pair of tension and moment that we can plot to see what the interaction between the tension and bending moments are going to look like. Same thing with weak axis bending. If we do that, if we, for strong axis bending, plot the pairs of tension on the y-axis with moment on the x-axis, we no longer get a linear line. This corresponds to the elastic superposition of bending normal stresses and tensile normal stresses. We actually get a slightly curved line. Down here we've got pure moment. We can't exceed the pure moment resistance. Up here we have pure tension. We can't exceed the pure tensile resistance. But now what we have is a nonlinear interaction between those two actions acting on the beam. And that comes from the coupled force presence and the plastic stress distribution that we'd consider for those forces. What S16 does, because this is a really complicated equation to figure out for all of our cross sections, instead they say, okay, this red line is pretty close to that nonlinear interaction equation for most of the space, right? It's mostly linear for a reasonable amount of time until it doesn't work anymore, right? Way out here, we're like, okay, this exceeds the moment resistance, so the red line doesn't work very well beyond this point. And so in addition to the red line, we're also going to use this black line. And the black line says we're also not allowed to exceed the moment resistance of the cross-section. what this works out to, this line is TF over TR plus MFX over 1.18 phi MP. That's down here, 1.18. So we're fitting two straight lines through this curve. One is TF over TR plus 1 over 1.18 is 0.85, MFX over the moment resistance MP. For weak axis bending, it's even more nonlinear. We can apply, even if we're very, very close to the full moment resistance of a section in weak axis bending, we can still apply upwards of 40% of the yield force as an axial load. Okay, so the relationship between axial force and bending moment is very, very nonlinear for weak axis bending. And we use a slightly worse linear equation to get down to about 1.67 MP, that's here. TF over TR plus 1 over 1.67 is about 0.6, so we get 0.6 MFY over MRY. And we also include this do not exceed moment resistance line. Okay. So what do we get? Well, we get a few linear equations that we're trying to use to approximate this nonlinear equation. In this region, we're slightly conservative, right? The real strength is somewhere up here. We're assuming the strength is here, and then everything under that line is the safe space. Okay. Up here, we're actually, when we get close to moment-only resistance, we're calculating the strength to be up here, whereas the real strength is somewhere down here. Okay, so in this region, we're slightly unconservative with this approach. We've got a full region where we're exceeding the nonlinear interaction curve. Do you think that's acceptable? It sounds bad, right? We're overestimating the resistance. But if you consider the limit states design philosophy, which states that on average, we expect the probability of failure to be less than, 0.01% or 0.1%, I forget what we said, but we have a certain reliability index. If you consider all possible combinations of MF and TF and the probability of getting that combination of MF and TF that makes this region happen, the probability is acceptably small so that we accept the slightly unconservative result because it's very unlikely to happen in routine practice. Okay, so it's not significantly adding to the probability of failure of our structures when we consider all of the other potential sources of error that would cause failure of our structures. Okay, so this is above and beyond kind of the, I don't know, a lot of people said don't present too much theory to me. This is a lot of theory just to show we use these two straight lines. And that's why when we look at these equations, we have these sort of weird factors of 0.85 and 0.6. And that's also why we have to check bending only. Okay, bending only is that straight black line that says you should not exceed moment-only resistance. And these are those other effective linear equations that are fitting a straight line through the first portion of these nonlinear interaction curves. Okay? Any questions about those concepts before we continue? Basically, you should have an appreciation now for why we're using all these different kinds of interaction equations. Okay? We have some interaction equations for class 3 and 4 beam columns that are based on what we talked about for elastic superposition. Then we have some for class 1 and 2 beam columns where we consider the plastic distribution of stresses. We have two equations to check in that case. We'll see how this works in an example. We've got a 7.5 meter long W610 by 153 that we looked at before in lecture 28. It's made from the same steel. Now we're going to assume it carries a factored bending moment of 1,000 kilonewton meters at the same time that it carries a factored tension force of 1,500 kilonewtons. And what we're going to do is determine whether or not the beam's strong enough under those applied loads. Does anyone have any questions about what the example is asking us to do before we get into any of these calculations? Okay, so this is a fun one because if you look back to your lecture 28 notes, we already calculated the moment resistance of this beam. The moment resistance of the beam was based on elastic lateral torsional buckling strength because the full section is laterally embraced. MU is 821 kilonewton meters. We took MR as phi MU, and we end up with a moment resistance of 739 kilonewton meters. At the same time, we're applying a moment to this beam of 1,000 kilonewton meters. So if this tension force was not here, this beam would not work, but the tension force is here. The question is the tension force enough to prevent lateral torsional buckling from happening? And is it small enough to prevent us from exceeding the yield stress on the bottom flange of the cross-section as well? So what do we have to do in this problem in order for us to answer the question? What should we start with doing, I guess, is the question I'll ask. Well, we need to apply the different interaction equations, right? So we already know from lecture 28, this is a class 1 section, okay? So we're going to have to check member strength, and we're also going to have to check the lateral torsional buckling resistance. Okay, so we have two checks to do, one for the bottom flange, one for the top flange, essentially. We already know from before that MR is 721 kilonewton meters, and we already know from before, because we had to calculate MP for this beam to figure out whether or not we were going to get elastic lateral torsional buckling or not, MP was 1,587 kilonewton meters. Okay? So the first thing we need to do is check strength. Okay? So basically what we're checking is strength. And I suppose in terms of a clause number, that's clause 13.9.2. We have TF over TR plus 0.85 MFX over MRX plus 0.6 FY over MRY has to be less than or equal to 1. Do we have any information at our beam that could help us out with this equation to simplify things before we get going? We have a TF, we have an MFX, do we have an MRY on the beam? It's not talked about in the question anyway. There's no weak axis bending moment acting on this beam, so we do not need to consider the weak axis bending component. What we do need to consider is TF, TR. Here we've got TF, where TR is calculated as phi AFY, plus we have 0.85 MFX over MRX. Again, when we're checking strength for combined loading, we're using the strength of a fully laterally braced beam, which is phi ZX FY for a class 1 section. We already have ZX FY here, right? That has to be less than or equal to 1. What we don't have right away is the area of our beam. We have to go look up the area in the handbook. If you go look up the area in the handbook for the section we're dealing with, the area is 19,600 millimeters squared. And so now we've got enough information to check the interaction equation. We've got TF, which is 1,500 times 10 to the 3. I'll write it as that. Newtons divided by phi A. Oh, no, I don't want to write that. I'll write it as 0.9 times 19,600 millimeters squared times 345, because it's A992 grade 50. So TF over TR plus 0.85 MF is 1,000. If we're going to go into Newton millimeters, we multiply by 10 to the 6. Divided by, and I suppose I could have left this in kilonewton meters, but we've got MP, which is 1587, so phi ZFY is 0.9 times 1587. I guess I'll write 10 to the 6 Newton millimeters. Doesn't really matter as long as you're consistent with units. That has to be less than or equal to 1. And what we get when we consider that interaction is 0.842, which indeed is less than 1.0. Okay? So, when we're checking members under combined loading, we check strength and stability. Because it's a class 1 doubly symmetric I shape, we're using clause 13.9.2, where we calculate strength this way. We have no weak axis moment, so that goes away. We get TF over phi Fy plus 0.85 MFX over phi ZX Fy. Has to be less than or equal to 0. When we calculate the combined ratio, we get 0.842, which is indeed less than 1.0. Okay, does anyone have any questions about the first part of that example? Is our beam okay so far? We're not exceeding the tensile strength limit of the bottom flange. That's basically what we just determined. Okay. Next, we need to check stability. Okay, so we check the flange in tension. Now we need to check the flange that's in compression. We need to check stability, okay, which in our case is going to be clause 13.9.3, which tells us that MFX over MRX plus MFY over MRY plus TF ZX over MRXA, minus TFXZ over MRXA has to be less than or equal to 1.0. Why are we using this? Because CSAS 16 tells us to, for class 1 or 2 sections, when checking the lateral torsional buckling stability of our beam, we use this equation where we're using Z to calculate moment resistance because it's a class 1 section. Again, we have no weak axis bending, and so we have MFX over MRX minus TFZX over MRXA has to be less than or equal to 1.0. MRX, though, is now calculated differently. MRX, when we're dealing with stability, is calculated in accordance with clause 13.6. We already calculated the moment resistance of this beam in lecture 28 in accordance with clause 13.6. Moment resistance is 721 kilonewton meters. Okay? So we already have enough information to go through and check. Oh, so why am I saying 721? 739 is the number. The ratio was still the same as last time, just changed the notes to 739 instead of 721. So now we've got MFX over MRX. I'll just write this in kilonewton meters to simplify, I guess. So we've got 1,000 kilonewton meters. MRX was 739 kilonewton meters. So right away, we think, okay, there might be some problems here. Before, when we were checking strength, MR was 1587 times 0.9. That was less than 1 already. We're already starting greater than 1, but we're going to subtract away the last component, and we're going to see what happens here. I've got, this is going to be important to make sure we get the units right here. I'll just write everything in Newton millimeters. That'll keep me straight anyway. So we've got 1,500 times 10 to the 3 newtons times Z. Z is also something we need to look up in the handbook for our section. Z is 4,600 times 10 to the 3 millimeters cubed. So we get 4,600 times 10 to the 3 millimeters cubed divided by MRX, which is 739 times 10 to the 6 Newton millimeters, multiplied by A, which was 19,600 millimeters squared. That has to be less than or equal to 1. just so you're not getting confused with units, you can write different units in these two, right? Because all the units cancel out anyway. So if you see me writing kilonewton meters and then Newton millimeters over here, it doesn't matter because all these cancel out anyway and we get a number that has no units. And so if you want to keep this straight in your calculator, you should make sure that you're using a unit set that you're comfortable with. So if we check that, we end up with a ratio of about 0.877, which indeed is less than or equal to 1. Okay, so even though we started out with a moment that exceeds the moment resistance, if there was no tension force, the presence of the tension force is enough to get us back down to a stress in the compression flange that won't cause lateral torsional buckling, and at the same time, it's not so much additional tension stress that we're exceeding the strength of the beam as well. Okay, any questions about that equation or that calculation before we continue? There's one last thing, right? And so I also need to make sure I'm not exceeding the bending only strength. And that only has to deal with not clause 13.8, but with clause 13.9.3 stability. It has to deal with the 13.9.2, which was the strength. MFX over MRX has to be less than or equal to 1.0. There's also an MFY term over MRY, but we already know MFY is 0 anyway. So we need to make sure that the moment resistance divided by the the factored moment divided by the fully plastic moment resistance also is not greater than or equal to 1. We've got 1,000 kilonewton meters divided by 0.9 times 1587 kilonewton meters. And it should be obvious, based on that equation, that that's going to be less than 1. We end up with 0.7, which is less than or equal to 1. Okay, so we had to check that. Again, I'll quickly go back here. This is where my PowerPoint starts to fail me a little bit here. That's why I wish I had my iPad with me. Oh boy, where's the mouse now? Okay, we'll try to go with this the fumbling way. We have to check the bending only strength again because we use basically the red equation here, the 0.85 MFX, and we were trying to make sure that we're not out here exceeding the moment resistance. Okay, so in addition to the strength, we also check the bending only strength to make sure that we're not exceeding the applicable limit of that straight line equation that we use to calculate the strength interaction for tension and bending. Okay? Are there any questions about the example, why we did the calculations we did before we move to wrap up lecture for the morning? Okay, so typical slide. Now we should be able to identify some elements that might be responsible for carrying combined axial loading and bending, describe the mechanics behind the interaction equations we talked about for strength and stability, and apply the linear strength equation, which is clause 13.9.3b, or clause 13.9.1 for class 3 and 4 sections, or the plastic strength equations, which is what we did today for class 1 or 2 beams, to check a member with combined tension and bending. Does anybody have any questions about anything we talked about today before we close things off? All right, well, we'll see everyone then this afternoon in lab.